right. So today is going to be an exercise in interpreting notation. We're going to look at something called the squeeze theorem and make sure that we can read this and understand what it's telling us. If h of x is less than or equal to f of x is less than or equal to g of x for all x on the open interval containing c, except possibly it's c, and if the limit as x approaches c of h of x equals L equals limit as x approaches c of g of x, then the limit as x approaches c of f of x exists and is equal to L. Perfect sense. Yeah? Okay. Let's talk about it. All right. H of x, f of x is less than or equal to g of x. What thing are we comparing here? Visually, when we're talking about h of x and f of x and g of x and saying one of these is less than or equal to the other, what is it that we're talking about? What values are we saying are smaller than the other? For all x on an open interval. So for all x, so that means we're talking about something on the graph. It's y values. Anytime you it is y values. Anytime you see f of x or g of x, remember we should be thinking y. So if you see h of x and f of x, then you should know that these are talking about y values. So in other words, we're talking about these y values, and we got three different functions, and we're ranking their y values from smallest to biggest. So we have a bottom function, a top function, right, because this is the largest, and then we have a middle function. And we know that it stays on the bottom, middle, and top because it says for all x. So that's the first part. That's what we're looking at. We've got three functions. One of them always stays on the bottom, one of them always stays on the top, and one of them is always in between the other. For all x in an open interval containing c, except possibly it's c. C is an x value. And we're focusing in on that specific x value and saying that h of x was which one? The bottom. And g of x was the top. And so we're saying that the limit of the bottom is equal to the limit of the top at a particular value. Then the limit of the middle exists and is equal to L. So in other words, it matches these limits. So this is the visual idea. I have a bottom function, a middle function, and a top function. So the middle function is in black, the bottom is in blue, top is in red. And so the idea is that if I have the bottom and the top function both going to the same value, and when I want to have the middle function put in between those two values and to stay in between those two values, well, if they're homing in on the same y value here, then there's nowhere else for this middle function to go. If it wants to stay squeezed in between those two, then it's got to stay in the same place that this top and bottom is going. There's nowhere else for the middle to go because they're closing in on that middle function. That's why it's called the squeeze theorem, because it's the top and bottom are coming and squeezing in that middle function. And this is used, this would be used to figure out limits that we wouldn't otherwise be able to figure out. There was one year, I think we'll probably actually do the free response, where they basically, they didn't say prove the squeeze theorem, but the free response basically walked people through how to prove it. And that was the question. Was like part C was talking about this situation, and then part D asked you to prove that the limit had to be the same as the top and the bottom limit. So usually what they'll do is we have one main example of a limit that we can prove by this squeeze theorem that we wouldn't be able to find the limit of with the stuff we talked about yesterday, which is the limit as x approaches 0 of sine of x over x. Limit as x approaches 0 of sine of x over x equals 1. And I might, if I have time, maybe that's what I'll do tomorrow. Maybe tomorrow I'll prove that this has to be the limit so you can see how it works. But we have, the way that it's going to work is basically we're going to have a top function we compare it to and a bottom function we compare it to. We're going to put sine of x over x in the middle. Say, hey, these limits both go to 1, so sine of x over x also has to go to 1. This also works if I have a constant here and the same constant here. So sine of ax over ax would also be 1. So that's the idea, is that we're going to look at these limits, and we're basically going to try and turn them into sine of ax over ax. That's what we're going to do. Question? Yes. A has to be the same value. So in this case, we can either try to turn this into sine of x over x, or we can try and turn this into sine of 5x over 5x. Well, bad news, we can't really be able to take a 5 and stick it inside the sine of x, so that's going to be more difficult. What we're going to end up doing is taking this 5 and turning it into a 1. So we have something that's sine of x over x. So if I want this to be a 1, what do I need to multiply top and bottom by? What would I multiply 5 by to get 1? It'd be 1/5. So on the top, what we're basically doing is moving where this 5 is. That's all we're really doing. This equals the limit as x approaches 0 of 1/5 sine of x over, the 5's cancel, and we have x. In other words, this is the same as 1/5 is on the top, so I can bring it out in front. I can take this limit, put it out in front. That's one of our properties of limits. 1/5 of the limit as x approaches 0 of sine of x over x. Bingo, we've turned it into sine of x over x. So we know what this is. It's 1. One-fifth times 1, so that's going to be 1/5. So this limit is 1/5. So again, our goal is to try and turn this into sine of x over x or sine of ax over ax. So we're playing around with the expression to get it to simplify the way we want. Let's look at a couple more. Let's start with the bottom one because it's most similar to what we just did. We either want to turn this into a sine of x over x, so either get rid of the 4x somehow on the inside of the sine, or we can take this and turn it into sine of 4x over 4x. Well, since it's a lot harder to bring something outside of the sine function, we'd need some double angle stuff and our trig identities. Or we can get a 4x on the bottom. So we're going to multiply on top and bottom. How do we make this 4x? What do we multiply by? 4. Multiply by 4 on top and bottom. Limit as x approaches 0 of. We've got 4 sine of 4x over 4x. So I can take this 4. This 4 here can come out in front of the limit because this is 4 times this limit, so we can take that constant and bring it out in front. 4 times the limit as x approaches 0 of sine of 4x over 4x. Ooh. Once again, there we go. Once again, that's 1. This is 1. So that's 4. Questions on that? So our game is to try and turn it into a sine of x over x, or to try and turn it into a sine of ax over ax. So in this case, we turned it into sine of 4x over 4x and used that to get the limit. Okay. I'm going to give 2 minutes. I want to see if we can figure this out. Limit as x approaches 0, tangent of x over x. I want to see if we can figure out what we're going to do to turn it into some kind of sine of x over x situation. This is the challenge. Put it in terms of sine of x over x somehow. Halfway through your time, how many have cracked the code? How many feel like they've got it? Okay. Here's my hint to you. We want to turn tangent into sine. We want a way to write tangent with something that has sine in it. We know something about tangent for how we can write it in terms of sine. All right. People at home are going to get to see it, but you guys won't yet. Oops. Yeah, that's better. Oh, move that. There we go. All right. I've gotten the answer. So that's your way to turn tangent into sine and cosine.